Hello, this is Mr. Crane, and this video is about P2, Radiation and Life in the 21st Century Science Suite. This video is to be used as a revision aid in addition to your revision guides, your workbook, and the notes you have made in class. Please do not rely on it solely to get you through the exam, but hopefully it will help you along. You could try watching this video several times, or maybe even once, and then just recording the audio and playing it back to yourselves. Either way, whatever works for you. Good luck. Light is a combination of electric and magnetic fields that oscillate in free space. They're received by our eyes and we detect them as a form of visible light. They're very, very fast. Around 300 million meters every second they travel, which is about 300,000 kilometers a second. Around the Earth about 7 times or so. And it can be generated in many different ways. Our sun is a very good example of this. It generates all types of light at all different frequencies. Light bulbs generate most visible light, not very much of other types of light. These frequencies stretch from radio waves all the way through to gamma waves, radio waves being the lower frequencies, gamma rays being the much more energetic higher frequencies. Radio waves are used for communication on Earth, generally between items such as walkie-talkies, TV, radio, and remote control key fobs that would open car doors, or indeed toys, planes and boats that you can control from a handset. Microwaves in high energy doses can be used to heat our food up, but in much lower energies are very useful in communicating with mobile phones, satellite dishes, Wi-Fi and Bluetooth. Infrared is used for us to communicate across the world through the means of fibre optics. It's also used more recently in airports to try and detect things underneath the clothing of people because it's less harmful than X-ray. Visible light is what our eyes are sensitive to, and we use it every day. It is also used in fibre optics as well. Ultraviolet light we commonly associate with the suntan. It doesn't have many other uses on Earth other than to emphasize a really bright colour in, for example, a disco or a stage show, or to try and make some colours seem more vivid so that they stand out. Some UV rays are quite dangerous. Some are quite safe. X-rays generally are very dangerous waves which can travel through our skin, bone, muscle and tissue. We use them in hospitals to try and pick out the silhouettes of our bones and the silhouettes of our tissues so that we can see inside ourselves. Gamma rays are much higher energy waves, and these can sometimes be very dangerous and destroy living things. On Earth, we only generally use them to destroy bacteria and harmful things such as those that might be found on medical equipment or in some foods. But even though our sun generates all these lights, only some of it gets through the atmosphere. Visible light, for example, the stuff that we see, quite a lot of it gets through. It's no coincidence that our eyes have evolved to be very receptive to it because it is abundant on Earth. UV light also reaches us and can help us with our suntan or make some of our clothes appear brighter when the sun shines upon them. Visible light can also be viewed from other stars in the sky, not just our sun. These stars, or distant objects in space that have reflection from starlight, can be viewed with telescopes. Although it is much dimmer, we can still see it if we magnify the image with mirrors or lenses. Sometimes visible light already on Earth can get in the way of this, such as street lighting or light pollution from car lights and other sources. Even though our eyes aren't receptive to it, radio waves can also be used to look at the universe. It can penetrate our atmosphere just like visible light can, and if we have the receptor, in this example a satellite dish, we can see an image just as plain as day. So what exactly does get through? Some light does, some light doesn't. It is the atmosphere itself which blocks some of these lights, but the atmosphere isn't just one thing, it's actually made up of several layers. Most of the atmosphere, however, is quite transparent to some UV light, to all the visible light range, with a little bit of infrared, and most of the lower frequency waves such as microwaves and radio waves. Gamma rays, infrared, X-ray and some of the UV are absorbed by the atmosphere. The ozone layer, for example, which is one layer of the atmosphere, absorbs harmful ultraviolet C rays. The ionosphere, which is much higher, the area where the space shuttle will fly in, absorbs the higher energy waves such as gamma rays and X-rays. Infrared waves are mostly absorbed by water, Water is found quite a lot in the stratosphere, which is where the higher clouds and most of our weather is formed. Some of the microwaves are also absorbed in there, and so we don't get every single microwave through, but there are no real defining limits as to what constitutes a microwave or an infrared. These are just guidelines. For those waves that can't make it through, however, we can't observe them on Earth, such as we can with radio waves, microwaves or visible light, and so we need to see them from a different perspective. We need to see them from outside the atmosphere. Infrared, UV and X-rays, we have telescopes which can look into deep space and put a UV filter or an infrared filter or an X-ray filter over it and take pictures in those wavelengths. This, for example, is a picture taken on Earth in visible light. It looks a lot different to a picture taken in infrared light. In infrared, the water is very, very dark. This indicates that it's absorbing a lot of the water. In visible, the water is much brighter. So the water must be reflecting some light here and absorbing some light here. Astronomers often use different wavelengths of light to study stars. Our Sun, for example, as one star, can be taken with many different types of filters. This is one taken in visible light, which we could take from the Earth's surface, and shows a couple of features of the Sun. These are called sunspots. If we took the same picture in a UV light, UV doesn't actually look this colour, it's just a fake colour, but in UV light it does show us a slightly different picture. In visible light, those sunspots appear to be colder areas or darker areas of the Sun, whereas if we look at it in a more energetic light, they actually seem to be a lot brighter. This would indicate that those sunspots that we thought about are actually energetic areas. If we took the same picture in X-rays, the image might look a little bit different. X-rays are much higher energy, remember, and so therefore this tells us a lot of information about sunspots. What we thought 50 years ago, when we thought sunspots were cold areas, are actually quite the opposite. Radio waves are the least energetic waves and don't really show too much when it comes to the sunspots. But as you can see, the 4 different pictures we have of the Sun give us more information as 4 than they do as 1. But not all surfaces absorb the energy and detect it. Here, for example, light beam number 1 is passing straight through an object. This would indicate that the object is transparent or translucent, so the light gets through. In the second light beam, the energy goes and stops in the object. This is an indication the energy is absorbed. That's what happens in our eyes. Light never shines out of our eyes, the energy goes in and is detected. In light beam number 3, the energy has been reflected off of the surface. This is what happens on shiny bollards, on the street surface, on grass. Everywhere you see an object, it is because light has bounced off of it. But what exactly is light? Sometimes it's viewed as a big wave that continuously goes on and on and on and on. Sometimes we could picture it slightly differently. It's a wave which is actually made up of many segments. Each of these segments contain portions of that wave. You could imagine it like a really long letter, or a letter that comes in many different installments. At the end of the day, you still get the same amount of light delivered. It's just a different way of looking at it. Scientists often use one way or the other way, whichever is more convenient. They call this wave-particle duality. It's not important you know exactly what that is, but basically it means sometimes seeing light as a wave, sometimes seeing it as a particle. Sometimes it's easier to think of it as a particle because when we consider the energy inside a wave, it's very difficult if the wave is very, very long. Whereas if we consider them as small tiny packets, for example the one on the left, if there's only 3 complete waves in there, we could imagine that wave, for example, has 3 millijoules of energy in. If we look at the packet on the right, that packet, for example, has 1, 2, 3, 4, 5, 6 bumps in it. This could have 6 millijoules of energy. Either way, looking at the two, it's clear to see that the one on the right is much more energetic than the one on the left. So whether it be fast or slow frequency, high or low that is, you could imagine it as a continuous stream or as multiple different streams. In this situation, it would be very easy to count the amount of energy that's been transmitted. If each one above, as we said before, has 3 millijoules, then the total amount of light delivered in these 4 photons would be 12 millijoules of energy. In the bottom, however, it would be much greater, 24 millijoules of energy. And this is important when we're deciding whether or not the light has delivered energy to an object, such as in ionization. Ionization is a method for heating up materials at an atomic level. The energies involved in ionization are very high, and therefore it affects the individual atoms and the electron shells around the outside of atoms. Atoms, which would naturally be bonded to other atoms next to it, could have their bonds disturbed by these ionizing waves. The bonds could then be broken and remade with other atoms to form in sometimes completely new materials. Not very good if it's ionizing a piece of DNA. To give an example, it's like having a completed puzzle and then removing a few pieces, twisting them around a short way, and then trying to push them back into the puzzle. Sometimes the materials are damaged beyond recognition. Waves that would cause this are the energetic waves from the UV band upwards. Not all UV is that dangerous, however. UVA is slightly ionizing and is quite safe to humans. UVB is a little more dangerous and would cause tanning. UVC is very dangerous, and fortunately it doesn't get through our atmosphere much. X-rays and gamma rays are also ionizing waves, and therefore it's advisable we try not to get too many X-rays as possible. It's also advisable to try and stay away from gamma sources, such as nuclear reactors. The former waves, radio, micro, infrared and visible, are all quite safe and heat up materials in different ways. Microwaves, for example, will vibrate particles so that they move. This movement in turn heats up the material. If it was some food, materials inside the food, the water materials that is, would heat up, and then that would in turn heat up the proteins and the carbohydrates, and the whole food would become warm. Microwaves would not heat up anything that isn't water, however. They're especially designed in the factory to only heat water. So it might pass straight through plastic or ceramics and glass without increasing their temperature at all. But remember, in the same way that food gets warm, water inside these foods or inside the glass could heat up the container. Microwaves are not absorbed by metal, instead they are reflected by metal. This is why microwaves cannot escape from a microwave oven, and there is a small metal mesh over the glass door in a microwave. This is to keep the waves in. The waves bounce around the oven and heat up any water in way. Usually water is inside the food.